So first of all, I'm honored to be here today. Thanks to Alex for the invitation, and also to the organizers. Like for us that are speakers, we get to enjoy the city, the conference. But there's a lot of people working really hard, behind the stage. So thank you a lot to them, and thank you for being in this presentation. Unfortunately, I don't speak Russian, so my presentation is going to be in English. Hopefully at some other point I will learn Russian and I will be able to do the presentation in Russian. So my name is Fernando Gont. I'm from Buenos Aires, from Argentina. I have done a lot of work on internet protocols. I have worked on everything from tools, patches for open source operating systems, and I have also done a lot of work on standardization. So this presentation the title is The Curse of Predictable Transient Numeric Identifiers. I know that the title sounds like a little bit complex, but as we get into the talk, you will see that the topic is hopefully interesting, but it's not that complex, at least not according to the title. And if you are old enough, or if you are into science fiction, this is supposed to be an image of Doc Brown from the movie Back to the Future. And the reason for which I picked this image for the presentation is that what I'm going to do during this presentation is essentially discuss problems that we have experienced over the last 40 years on the topic of transient numeric identifiers. I will try to analyze the reasons for which we experienced these problems, and try to figure out if there is an alternative path, like if there's anything that we could do in a different way to actually avoid these problems in the future. So, okay, not this one. Okay, there you go. So, introduction to to this topic. Essentially, you might wonder, okay, what are transient numeric identifiers? These are identifiers that the short version of the story, or a simple way to look at them, is that they are normally or usually numeric values that are used to identify protocol elements that only last for a short period of time. It's easier to think about these identifiers with examples, okay? Among the examples are, for example, TCP initial sequence numbers, IP identification value, DNS ID, IPv6 interface ID, and so on. So these are the kind of identifiers that we refer to as transient numeric identifiers. And you might wonder, okay, what's wrong with this, or what is the issue with these identifiers? Well, the issue is that over the last 40 years, we got, for the most part, these identifiers wrong, okay? Now, you might wonder, okay, you are saying that we got this wrong. What do you mean by wrong? Well, wrong means, in this case, that we have selected these identifiers in a way that they have negative security or privacy implications. These are some of the examples that I could provide. There are many, many others, but this is just to give you some idea, and I will try to stress on a couple of examples that are super simple. Let's think for a second about MAC addresses, okay? The only thing that you need about a MAC address is that the MAC address is unique. Now, that has changed over time a little bit, but for most systems, or traditionally, you use a MAC address that is globally unique and constant. So no matter which network you connect to, you always end up using the same MAC address. That's like a serial number for your device. And obviously, that identifier will leak the identity of your device. So if I see your MAC address in this network, and then eventually all of us, we travel to a different network, and I see the same MAC address, I can infer that it's actually the same device, okay? And that's not really needed. The same thing has happened for other identifiers, like, for example, IPv6 interface identifiers. So a lot of implementations, they select identifiers in a way that they are predictable. And that means that, for example, you can leverage these identifiers for host tracking, and that you can also do or implement IPv6 address scans. The same thing applies, or a similar thing applies to a bunch of other identifiers. TCP initial sequence numbers. Like if these identifiers are picked in a predictable way, then you can spoof connections or perform, for example, data injection attacks. Now, one thing that is important is that these negative security or privacy implications were not really warranted. So it's not that we needed the identifiers to be bad. It's just that we did a bad job at selecting these identifiers, and as a result, we have experienced these negative implications. Now. No, this is like a summary, or tries to be a summary. Like, when I was introducing the topic, I mentioned that we have experienced, problems with transient numeric identifiers for 40 years. And that might come across as an exaggeration, right? Like, okay, it can be possible that for 40 years we hit the same problem. Now, in order to prove the point, what I tried to do is a timeline, okay, of some of the events associated with predictable transient numeric identifiers. This is by no means complete, okay? It's just like a sample of different kind of protocols and different things that were found over time, so that you can look at that and look at the dates and say, okay, well, that looks like true. Like over the last 40 years, we hit the problem over and over again. So I'm not going to go into a lot of detail about this, because for the most part, the whole point of this slide is to prove the point that over the last 40 years, we hit the problem 100 different times. But just to give you an idea, I believe the first, let's say the first document or the first instance of this problem that I could find was as far back as 1985. And there was a paper by Robert Morris where he essentially found that BSD implementations, they were using predictable TCP sequence numbers. So that document was published in 1985, okay? Vulnerability found in BSD systems. Now, 10 years later, we are jumping to 1995. Tsutomu Shimomura, he published a document where he was documenting an attack that allegedly had been performed by Kevin Mitnick. That's what he said, at least, where Kevin Mitnick, he exploited the vulnerability that had been discussed in 1985, but that had never been actually fixed, to actually perform a real-world attack. 10 years later. Something that was documented in 1985, nobody did anything about it. 10 years later, there's a real-world exploitation of that problem. In 1996, we can see that OpenBSD, they produced the first implementation of port number randomization, okay? So they were the first ones to try to do something about this topic in a proactive way. Then we can see in 1994, Salvatore Sanfilippo, he found that there were implementations that were producing predictable IP ID values. And as a result of these predictable values, your system could leak out information, for example, about the rate of the packets that the system was transmitting. 2001, Thomas Narten and other people, they found that because of the way in which IPv6 interface IDs were being selected, hosts could be tracked based on the IPv6 address. 2001, look, there's like 15 years later, there's work by Michal Zalewski where he found that there were most of the TCP implementations, they were generating predictable initial sequence numbers. 2004, I did work, that's over 20 years ago, where I documented, these were known at the time, I documented ICMP attacks that could be leveraged for performing denial of service attacks. And these attacks relied on implementations using predictable transport protocol ports, okay? 2007, Amit Klein found that there were implementations that, in theory, they were randomizing the IP ID value, but they were using flawed algorithms. So they were producing predictable IPv6, predictable IP IDs. 2008, for those that were around that time, that was the year where Dan Kaminsky released like what became known, I believe, one of the most publicized network-based attacks, a DNS attack that you could perform a DNS cache poisoning. And the attack in question that was publicized or was made public in 2008 relied on implementations employing predictable transport protocol ports and predictable DNS IDs. We keep going. In 2007, Amit claimed phone again. Implementations were generating IP ID values with flawed algorithms. 2011, I found that IPv6 implementations were generating IPv6 IDs with wrong algorithms, and I also found in 2011 that because of the way IPv6 addresses were generated, you could perform IPv6 address scans that were deemed to be impossible, but because of the way the addresses were generated, they were made possible. 2016, I also found that something that is called IPv6 privacy extensions also had problems with the way the identifiers were selected. And the thing goes over and over and over again, okay? The whole point of this slide is to look at the timeline and say, okay, yeah, it looks like for the last 40 years we hit the same problem over and over again. Now, let's talk a little bit about the motivation, and this is not just some random slide that I introduced, but it's actually what was our motivation for doing this work. And when I say we, it's because this work was carried out by Ivan Arce, a colleague from Argentina, and myself. And when it comes to the motivation, the idea is very simple and straightforward. We had worked already quite a lot on actually addressing this problem on multiple protocols. I author or co-author all the RFCs that you see on this slide. For example, 6056 for port number randomization, etc., etc., etc. That means that I had found problems associated with predictable IDs in different protocols, and I had done the work to actually fix the specification for the problem to go away. Now, what we found, or what we were thinking about, is like, okay, we are playing like whack-a-mole, okay? Every single time there's a new protocol, the protocol suffers from the same problem, and we have to work on a solution for that specific protocol. So what we were wondering is, well, why in the first place we keep finding the same problem over and over again, okay? Is there anything that we could do so that rather than all the time working on a new protocol and try to publish a new specification and fixing the specific problem, to try to figure out if we could do something to actually address the root cause and, solve the problem, forever, so to speak, hopefully. And so this is let's say, the challenge that we set out to solve or to address. We wanted to do stop doing fixes on protocol by protocol basis, try to figure out, okay, how come that over 40 years we keep hitting, the same problem, and is there anything that we could do to actually, stop this problem from happening over and over again? So the first thing that we did is try to let's say, analyze the reasons for which these problems were affecting protocols in the first place. And what we did, this is not something that we just got together and did, and we came up with a conclusion, but what we did is we analyzed as many IDs as possible, as many protocols as possible, and tried to figure out the reason. And the reasons that we found, or we believe are the root cause for these problems, is that three different reasons. First one is that interoperability properties for these identifiers, and I'm going to explain what I mean by this. Interoperability properties for the IDs were not clearly specified. Second reason is that some specifications, they just recommended, wrong algorithms. So the advice that you'd find in the specification itself was wrong, period. And third reason is that there were implementations that were simply failing to follow the advice, in those cases that the protocol specifications were providing the right advice. So let's go through each of these in detail. So the first one that I mentioned was failure to specify the interoperability requirements. So when I started talking about these IDs, I said, okay, well, these transient numeric identifiers, they identify protocol elements, and I provided examples: transport protocol ports, DNS ID, IP ID, and so on. Now, obviously, the idea here, or what should be the case, is that there are requirements for these IDs. So these IDs should have certain properties. And the properties that these IDs should have depend on the specific use case, okay? For example, for some IDs, the requirement could be uniqueness. So you need a unique value, that's it. For other cases, you might have a requirement where, when you generate subsequent IDs, they have to be monotonical increasing. Monotonical increasing means if you select an ID, the next number should be equal or larger, okay? Like a linear function, so to speak. Another, interoperability requirement could be for the IDs to be unique and stable, etc., etc. So that's, interoperability requirement. But then there's a different question. What could happen if I fail to comply with the interoperability requirement? For example, the spec says you need to pick a unique value, and you just fail to pick a unique value, okay? And this is where the failure severity comes into place. Failure severity means, okay, how bad things are if you fail to comply with these properties. So there's an ID that is supposed to be unique, okay? But you fail. You select a value that was already in use. Well, if it's a soft failure, that means that it's mostly okay, okay? So you didn't comply with the interoperability requirements, but the protocol doesn't fail badly. On the other hand, a hard failure severity, as the name implies, means that, yeah, if you fail to comply with the property, the protocol breaks badly, for some meaning of badly. Now, the problem with a lot of specifications is that they fail to specify these requirements. So you have a protocol that tells you, okay, you need to pick a port number, and if you are an implementer, and you say, okay, well, which algorithm should I use? Well, you have no clue, because the spec doesn't say what are the properties that the ID should have, okay? So you don't have much of a criteria to select an algorithm. You don't really know what are the properties that the ID should have. Second reason for these problems that I mentioned was specifications providing the wrong advice, okay? And I can, provide like simple examples. There are implementations that they simply recommend the wrong algorithm. If you look, for example, at RFC 791, the IPv4 specification, or 2460, which is the former IPv6 implementation, they essentially say that you should set the IP or IPv6 ID with a global counter, period. So that's the advice that the specification provides. Meaning, if you follow the spec, you will actually introduce the problem. The spec is actually providing the wrong advice. Same thing for the TCP implementation. Now this has been updated, RFC 793, but if you look at 793, it essentially says that you should pick the initial sequence number with a counter, global counter. Of course, meaning it's going to be predictable. So if you follow the spec, you actually introduce the problem, okay? Now, that's one of the possible scenarios, specifications providing the wrong advice. Now, there's a second case, which are implementations that just fail to provide a recommended algorithm. And there are two examples. There are many more, but this is just, just to mention a couple of them. If you look at, for example, the TCP specification, RFC 793, it fails to recommend an algorithm for selecting port numbers, the ephemeral port numbers, the client-side port numbers. So it doesn't provide any advice. And what happened in the real world, that most implementations, they ended up using a global counter. Just a simple algorithm that works, if you wish, but has security and privacy implications. In a similar way, you have RFC 1035, that's the DNS specification, and they failed to recommend an algorithm for generating the DNS ID. So they specify the value, they specify the protocol field, if you wish, but they don't provide any kind of advice when it comes to how to actually generate that value. So implementations are on their own. And in a lot of cases, what happened is that the folk that is actually working on an implementation, they are working on tons of different things. And they are not going to spend a whole time, okay, there's an idea that I should specify here, what would be the best, the best algorithm. I will come up with something that works and move on to the next thing that I need to implement. In a lot of cases, history provides examples of that. Normally this thing of coming up with an algorithm that works, has led to implementers picking, the wrong algorithms. Last but not least, you have cases where the specifications, they provide the right advice, but implementations just decide to do something else, okay? In some cases, because they found a shortcut and say, oh, that's complex, I want to do something that works, but it's not as complex. And there are other cases where maybe you had a protocol specification that was providing the wrong advice, okay? Eventually, the specification was updated, but even when the spec was updated, the implementation wasn't updated yet. And that's understandable, okay? There's obviously a delta of time between when a specification gets published and when actually the specification gets implemented. So that's kind of like our analysis of let's say, the root cause of the problem, okay? 3 different reasons. Now, that's okay. That's like fine for understanding why we have the problem that we have, but that doesn't solve the problem, okay? So essentially, we said, like, okay, what could we possibly do to actually prevent this problem from happening again? And our idea was as follows. So we said, why don't we try to come up with a taxonomy? Okay, with a taxonomy for transient numeric identifiers. So what we did is we collected as many transient IDs as possible. For example, transport protocol numbers, DNS IDs, IPv6 interface identifiers, etc., etc., etc. And we tried to analyze, we didn't know if that was going to be possible or not, but we tried to analyze if we could come up with some categories, hopefully a few of them, not that many, where we could group all of these identifiers. Okay? This is not something that we thought that we could do. It was just, okay, let's try. Now, what was the goal with that? Because, obviously there had to be a reason to try to do that. So our goal was to say, well, if we can actually come up with a taxonomy saying, okay, virtually all of the identifiers that we know, follow into this small number of categories, then what we could do afterwards is try to, let's say, design or come up with an algorithm that could generate those IDs in a way that they didn't have negative security or privacy implications, okay? It's like saying, okay, we have like 15 different, types of, for 15 different, transient IDs. We found that we can group all of them into, let's say, 4 or 5 categories, and then say, okay, what would be a good algorithm for generating, identifiers of this category? So the idea was that in the future, if our taxonomy was good, then every time that there was a new protocol that was specified and there was a transient ID that was needed, then a protocol specification could look at our taxonomy and say, well, this identifier falls into this category, so the right algorithm to generate the ID is this one, period. Okay? Making things easier for protocol specifications, but also for implementations. If, let's say, you are an open source developer, if you have the requirements of, what are the requirements that the ID should have, you go to our taxonomy, okay, this is this type of requirement, this is the algorithm that I should implement, period. So that was the goal. So this is the taxonomy that we came up with. Of course, the taxonomy is based on 2 things. First thing is the interoperability requirement, what property this ID should have. An example is uniqueness, okay? And the other property is the failure severity. So, for example, category number 1 means that they are identifiers that have the requirement to be unique, okay? But they have a soft failure severity, meaning if you select an ID and you just happen to pick the wrong number and you are reusing the number, it's okay, because it's a soft failure severity. Then category number 2 is uniqueness, but with a hard failure, meaning that you have to pick a number that is unique, but it's not okay if you happen to pick the same ID, because the protocol breaks badly. Third category is uniqueness. Okay, you want unique values that are stable within context. And I know, obviously, that this is like, okay, what do you mean, uniqueness stable within context? The simple example that I could provide with this is, for example, of stability within context. You could imagine, for example, a system that needs to pick an address, okay? An address. So you connect to a network. The context in that case would be the network, okay? And you want the system to pick one address. If the system moves to a different network, you want the value, the ID, to be different. But if the system goes back to the original network, meaning the context is the same, you want the value to be the same one as before, okay? The last one, category number 4, is uniqueness. The values need to be unique, and as you can see here, uniqueness is in, the requirement for uniqueness is in all cases. But you want values that are monotonically increasing for a given context. That is that in a specific context, the values should grow over time, okay? And what we did, because this is like what we could do to actually try to figure out if the taxonomy was good, we came up with these 4 different categories, and we went through as many IDs as we knew. IPv6 flow level, DNS ID, IPv4 ID, IPv6 ID, ephemeral ports, blah, blah, blah. And we tried to figure if those identifiers would fit into our taxonomy. Obviously, if we could find an identifier and it's like, okay, well, it's not category number 1, 2, 3, or 4, well, then we had a problem, okay? But at least when it comes to all of the identifiers that we covered, we succeeded in that respect. Now, what I'm going to do now is I'm going to quickly go or briefly go through each of these categories, and I will do 2 things. First one is to try to very quickly, show a possible algorithm, like a simple algorithm to generate IDs for that category in a way that the IDs don't have problems, okay? In some of these cases, there are let's say, simpler versions and more complex versions of the algorithms. I will cover the most simple ones because we cannot spend a lot of time on each of them. And then I will try to provide an example of how this would apply with a real-world example. Okay, how we use this algorithm to generate whether that's a TCP port or an IPv6 address or whatever that is. So, first example is uniqueness with soft failure severity. What does this mean? We need a unique number, but if we happen to pick a number that is already in use, it's okay. Now, this makes things way easier, because we're saying, okay, you want to pick something that doesn't follow a pattern, okay? That makes you think that you would probably want to randomize the value. And we are saying, if you happen to pick the same value as before, you happen to reuse a value, it's okay. So what do? You just pick a random number. Obviously, when you get to implement this, there's a few details, but they are obvious. A lot of cases, you have protocols that say you have to pick a random number, but between this value and that other value, okay? So you just don't call random, you need to adapt the random value within a given range. And also there are other details, like in some cases you can detect whether the value is in use already. Now the question is, if you pick a random value and you detect that the value is in use, what do? Well, 2 possible options, or 2 possible obvious options. One is to pick another random value, but you could be there forever, because if there's so many values in use, you keep picking values that are in use. Or what most implementations do for these things, first of all, you pick a random value, and if it's in use, you use the next value in sequence. Okay? That's it. This is, for example, what some implementations use for generating the DNS IDs, for example. Okay? Now, I was mentioning that I would provide some real-world examples of this, of where or with which protocols you could use these algorithms. One example for this first category, uniqueness but with soft failure severity, is DNS IDs. And what makes it probably, is, there you go. what makes it easy to see, how the values are generated is to look at, this timeline. So what we say here is at time 1, we need to pick a DNS ID. Obviously, what do? We just pick, a random number. Time 2, we need to generate another one. And what we're doing here is just picking random numbers, okay? So there's no correlation among them. If we just happen to reselect a value, as I said before, it's okay, because it's a soft failure severity. So this first category, it's like very easy. Pick a random number. If you happen to pick a number that is already in use, it's fine, okay? That's category number 1. Category number 2 is slightly more complex. Why? Because we say that we want unique values, but if we happen to select a value that is already in use, the protocol breaks badly. So you can't just pick a random value, because probability, from the point of view of probability, you could just be unlucky and happen to pick a value that is already in use, and the protocol would break. Spoiler, what implementations normally do when you need to pick a unique value but with a hard failure severity, they say, well, the best way to avoid selecting the same number again is to actually come up with a monotonical increasing function. The simplest implementation would be a linear function, okay? So rather than picking random values, what you do is you pick incremental values. And the idea is that in that way, obviously you have to select or use every single value in the sequence before you actually go back and run the risk of reusing a value. One possible way to do this, and I will go through this expression in a few more slides in more detail, but one way to do this is generate these values as a result of computing a hash function over a context, whatever context is, okay? This could be the prefix that is used in a network, whatever that is, a secret value. Obviously, it's supposed to be a cryptographically secure hash function. You use a secret, and then you use a counter. So the idea is that obviously this part that you have here is what makes the values unpredictable, because you don't know if the hash function is cryptographically secure and the key is not known to the attacker. You don't know what is going to be the output of this expression. We will see that the algorithms that you end up using in practice for category number 2, which is uniqueness but a hard failure severity, is the same algorithms that we use for uniqueness monotonical increasing, okay? So that's why I will not go into further detail as of now. Next category that we have is stability, uniqueness, but stable within context, okay? And this is obviously, the name sounds more complex than what this actually is. So let's think about the example that I provided before. Let's say that we want to generate, let's say, IP addresses. And we want, whenever a system, let's say whenever I connect my mobile phone to this network, I want my mobile to always get the same address, okay? Why? Normally because that's important for operational reasons. Like if you want to do network activity correlation, it's interesting if the devices always get the same address. But we don't want the host part to be the same when the device changes to a different network, okay? We want that to change. The way to do that is super simple. What we are going to do is, and let's say the whole algorithm is essentially the first expression. What you do is you generate the ID by computing a hash over the context. Context, we are going to see examples, okay? That's going to depend on the use case. Second, we are going to put a value that I will call R. That's going to be a counter, and I will explain what that is used for. And then a secret. Okay, that's what makes the values unpredictable. Now, the idea is simple. We compute a hash with a secret key, so it's impossible to actually predict the values. Obviously, as long as all of the arguments to the hash function are the same, the result is going to be the same, okay? Now, you might wonder about this parameter R in the middle. And the reason is, like, let's say that I compute an ID, okay, for my mobile phone, and I detect that that value is already in use. Let's say that I can detect that. Okay, what could I do to actually generate a new one? And this is where the value R comes into place. So if you selected a value and it's already in use, and you need to select a different one, just increase the value of R, and you get a new value, okay? Now, this is, it becomes more, more obvious and more evident when you see an actual example. And there are two different examples that we can use for this. One is IPv6 addresses, and the other is MAC addresses. So if you use a device, and you may have seen that your mobile phone says like, we can randomize the MAC address. So they use an algorithm such as this, okay? So what we want, both for IPv6 addresses but for MAC addresses, is you want to use, when you connect to the same network, you want to use the same address. But if you move to a different network, you want the address to change. And you might wonder, okay, why don't we just, for example, randomize the MAC addresses, okay? Well, the reason is operational and practical. For example, in a lot of cases, when you connect to, let's say, a public Wi-Fi, so you authenticate with some captive portal, and the captive portal, writes down or notes or records your MAC address. If your MAC address were to change all the time, every single time that you connect to the network, you'd have to re-authenticate, because the network would think that it's actually a different device. So that's why you want addresses that are stable within the same network, but that change when you move from one network to another. So let's provide, one example which makes this like super evident. Let's say that we want to generate an IPv6 address, okay? IPv6 address, the way in which you generate an IPv6 address is essentially you have a prefix, that is the prefix that is used for the network, and you need to generate an ID, an interface ID, which is like the host ID part. Now, let's say for the sake of the example that at time 1, you connect to some network. In this particular case, the context is going to be the prefix that is used in that network, whatever that is. So if we need to configure an IPv6 address, we are going to compute the hash over the prefix and a secret, okay? Secret obviously is going to be like, obviously, unknown to the attacker, but stable. In this case, of course, you may see that I'm simplifying the algorithm. I'm not adding the counter or anything, just for the sake of, brevity. So we compute the hash over the prefix and the secret, and we get some value, this value that we have here. So the idea is that for that prefix in that network, we would configure the ID to the first one. Now at time 2, we move to a different network, totally different network, which uses a different prefix. And we need to configure an address there. What do? We compute the same algorithm, hash over the prefix and the secret. We get a different ID. This is how we configure our IPv6 address. At time 3, you can see here, we go back to the original network. We are going back to the network that uses prefix 1. And obviously, since the parameters for the hash function are the same, you see that we end up generating the same value. So the algorithm doesn't need to record what is the value that you generated before, because as long as you use the same parameter for the hash function, you get, the same result. And in this case, at time 4, what we do is we move to a third network, prefix 3, and obviously we see that in this case we compute a value that is different from the previous cases. This is the algorithm that is used for generating nowadays, that it's used for generating IPv6 addresses and also for generating MAC addresses. So if you look at the device and you say, okay, I see that my MAC address changes, but in some cases it's a value and in some cases it's the other, because MAC addresses are generated like this. Obviously, in the case of MAC addresses, you don't use a prefix, but you use the SSID, okay? In that case, the context is the SSID. Okay. The last of the algorithms, and this will be essentially an extension of the algorithm that we just saw, is IDs that are monotonically increasing for a given context. Given a given context, we want values that are incremental. And the algorithm for this category is super simple. It's essentially the same algorithm as before. As you can see on top of there, it's a hash computed over the context, wherever the context is, and a secret key. The only thing that we make different is that now we add a counter to the result of the hash function. so that rather than being stable values, since we are using a counter, every time that we generate a value, it's going to be incremental. Not stable, but incremental. Examples that, where this algorithm is used. Without getting into the details, what TCP timestamps are, let's just say that there's something in the TCP protocol that is called a TCP timestamp option. Okay, the details they are not worth discussing in the context of this presentation, but these are IDs that have the requirement that they have to be monotonically increasing for a given context. Now, what is the context for the TCP timestamps? Source address, source port, destination address, and destination port. Now, the idea is simple. If that is the context, every time you select a timestamp for a combination of these values, it has to be monotonically increasing. So how are TCP timestamps generated? Essentially, you compute the hash function over the context. This is what I said before, the secret, and you add to that a timer because you need the values to be monotonically increasing. And this is very easy to see, or easier to see, when you look at a concrete example. This is some sample output. So let's say that at time 1, we need to generate a timestamp for a given context. Given context means specific source address, specific source port, destination address, and a destination port. Now, as long as those values are the same, we say that that's the same context. So for context 1, we compute the hash function and the timer, and let's say that we get this timestamp here, okay? Now, at time 2, the context has changed. This could mean, for example, that we are connecting to a different service, like the destination port change or that the destination address change. The whole point is that the context now is different, so at least one of these values has changed, okay? Now we generate the hash function, which is going to be like a completely unrelated value, and let's say that we get this result, okay? Time 2. At time 3, if you look at the arguments, now we have the same context as in the previous case. Okay? Now, obviously, the result of the hash function here is going to be the same result as here. Why? Because the arguments are the same. Now, what has changed in the expression is that since we are using a timer, the idea is that this timer is increasing. So when you look at the output of the algorithm, you can see that the value looks similar. Okay, it starts in the same way, but this value is actually larger. Why? Because the result of the hash function was the same, but since you are using a timer, it's increasing over time. Okay? And then at time 4, you are using a different context, context 3, and obviously the result is completely unrelated. So these are just, and this is a concrete example, this algorithm that I'm discussing here is, for example, the algorithm that is currently being used to select TCP timestamps and also to select TCP initial sequence numbers. So this is not that I'm saying, okay, that's a nice algorithm or an algorithm that I like, but nobody uses it. It's actually in use. Now, I was saying before, when I was covering category number 2, that was uniqueness, but with a hard failure, I said, spoiler, the algorithms that we will use for this category are the same ones as for category number 4. So I will provide an example here. One of the examples of an ID, a transient numeric identifier, that has the requirement of uniqueness, but with a hard failure, are port numbers, like TCP source port numbers. If you happen to pick the wrong port, you reuse a port, the protocol fails, okay? So you need to select port numbers in a way that somehow you are guaranteed that you are not selecting the same number again. So in practice, you cannot just pick a random number, because if you are unlucky, you pick the same number, the protocol breaks. And this is not just theory. There are examples where, for example, when you have like two systems that issue like a lot of connections over time, if you just do one connection every now and then, it's okay. But when you do a lot of connections that all the time you are generating IDs, this has been found in practice that implementations that try to just randomize the port, they run into issues. So in this case, if you want to select source ports, the context is going to be source address, destination address, and destination port. Meaning that if you want to connect to this destination address, this destination port from this source address, you want to do multiple connections, over time you want to pick values that are unique. How do you select these values? For example, in the case of port numbers, we're going to compute the hash over the context. Context, again, source address, and destination port, a secret, and a counter. So let's say that we are issuing a connection to a specific context, a specific system, a specific port, and let's say that we picked port number 10,501, okay? Now at time 2, we connect to a different endpoint. Could be a different system or a different point, a different port. The context has changed now, so we pick this other number. In this particular case, this is a spoiler if you wish, it's a simplified version of the algorithm, so this counter is global. Normally in practice you wouldn't do it, okay? Now, for context number 2, you pick a different port, totally different, 1043. At time 3, we want to select the port number for the same context as in the previous case. The result of the hash function is going to be the same one as in the first case. But now, obviously, this counter has changed. So now you see that this value kind of like follows the same sequence, okay, which is totally different from this sequence. And in the last case, time number 4, we select another port for context number 2, and you see that this port number obviously follows the sequence of the first one. This is, just to give you an idea, the algorithm that Linux uses to generate source port numbers. So if you're looking at your connections and you see, okay, that's kind of like weird because it's like, in some cases, looks like there's a sequence, and in other cases, it's a different sequence, it's because of this algorithm. Now, I mentioned, and I'm not going to go into a lot of details, but I mentioned in the previous slide that, okay, the counter is global. And that may give you an idea of, hey, you are saying that you don't want values to be predictable, but you are using a global counter there. So that's something that you can avoid, and one possible way to avoid that is to use something like this. You use the original hash function as before, but rather than using a global counter, you use the second expression that you have there, which is you compute a second hash to have an array of counters. And you can have as many as you want, okay? So the idea is that you have the first hash function as before, but now, rather than using a global counter, you use like an array of counters. This is just, let's say, an improvement over the previous algorithm, but the idea is the same. Okay, so this is the work that we did, or with my colleague. We actually worked for over 6 years on this. I don't know if that's a good thing or a bad thing, but we work a lot of time. And I would say that, when it comes to things such as, for example, protocols, you can do a lot of interesting work. You can come up with a lot of interesting ideas. I'm not saying that this is an interesting idea, but the thing is that you have to somehow find a way to apply these ideas to the actual implementations, okay? Because if I would just come here and present this work, and we don't do much more than that, then nothing would really change. So what we did in this respect is to we publish a document at the IETF. IETF, it's the Internet Engineering Task Force, the organization that standardizes Internet protocols. And that initial document over there, that's the name of the file, because these documents are public. So if you Google for that, you will find the document. So we originally came up with a proposal that essentially included everything that I explained in this presentation. So we started with the timeline. In that document, you can find the timeline even with more examples. Okay? Then we proposed the taxonomy, and we came up with recommendations. But you know, standards organizations have complex processes, so a lot of times there's politics, there's processes that need to be followed, etc., etc. So over time, after 6 years, 7 years, our initial document was published as 3 different RFCs. Okay? First one, what is, formally speaking, is an Internet Research Task Force document. First one, 9414, which is a document that includes the timelines and the discussions, the historical perspective on this topic. Okay? The idea was to document, to have a way to documenting, like, okay, this is a problem that we have. So at least you know, it was documenting. We could, even if we fail to provide recommendations, at least there would be a record that, okay, look, we have been screwing up for the last 40 years. That's document number 1. Second one is 9415. This is the document where we document the taxonomy, the same stuff that you saw in this presentation, obviously just with more details, and we come up with algorithms. Obviously, I provided like a, let's say, a simplified discussion of the documents. Then when you have to implement those things, there's a lot of stupid and, you know, small details that you have to take into account. So in that document, 9415, you will find all those details. For example, if you need to generate a random number, which are the functions that you should use, because not all functions are good. If you have to, let's say, pick a number within a specific range, what's the correct way to do that? There's a lot of tiny details that they don't change the underlying idea, but you know, if you need to implement this, you have to figure out those details. And the third document, I believe that in a way is the most important of the 3 documents, because it's the document that introduces formal requirements for protocols. And I don't know if it's a good thing or a bad thing, but there have been essentially only a couple of documents that have, let's say, have introduced requirements, security requirements for protocols. So I will just focus very briefly on the requirements that are introduced by RFC 9416. If you see, you know, this part of the text in capital letters is because IETF standards use, you know, terms in capital letters when they are formal requirements. So what we said is the requirements that we introduce is, the first one is that if you are specifying a protocol that employs or that defines transient numeric identifiers, you have to specify the interoperability requirements, okay? Whether, you know, that's uniqueness and what is the associated failure severity. In a way, that's going to be of use because when you specify the interoperability requirements, for example, uniqueness, hard failure, you will be able to map your ID to the taxonomy that we introduce, okay? That's requirement number 1. Second one is that you should do a vulnerability assessment of your IDs, meaning in your protocol, you should analyze what would be the problem, for example, if the values were predictable. Depending on the protocol, that will change. Maybe if you know, it's a protocol, transport protocol like TCP, if the values are predictable, that might lead to data injection attacks. If it's a different kind of protocol, it could lead to tracking or a number of other things. Third one, which is obvious, you could say, is like you should never use transient numeric identifiers that are predictable. Because obviously the whole point of this presentation is that predictable transient IDs are bad. Then we get this other requirement that says that if you have a protocol spec, okay, that is specifying a transient ID, you should recommend an algorithm. What we suggest is that since we have the taxonomy with recommended algorithms for each category, you point to one of the algorithms that we have specified. If you want to specify your own, that's good, but at least by default, you should refer to the algorithms that we have specified. And the last requirement is that you should follow these recommendations even if you are using a protocol that uses cryptographic techniques. Now, the reason for this is that I will provide a short background. Like, while we were working on this, the IETF was working on the QUIC protocol, which you might know is a transport protocol that nowadays is employed quite a lot for web transfers. It's based on UDP and blah, blah, blah. And there were people that said, like, we're using TLS, so we don't need to care about this. Now, in practice, you do need to care. Just to provide one simple example, if you're using TLS, okay, TLS works on top of TCP. So if the TCP initial sequence numbers are predictable, you can still attack the protocol, maybe for denial of service. Why? Because TLS, needs to operate on top of TCP. So that means that, TCP-based attacks are, still valid or important, even if you're using TLS on top of TCP. Okay, so what are our conclusions of this work? So I believe it's clear, even from the timeline that I showed in the first few slides, that predictable IDs is something that has plagued implementations and specifications for 40 years, and the timeline was essentially a data point, so it's not that I'm just making this up. There had never been an effort to actually try to tackle the root causes. We had done a lot of work to fix specific protocols, but there was never any work trying to say, like, okay, how come that we always, run into the same problem for every single protocol? Even at times, for example, these problems were affecting IPv4, then the IETF produced IPv6, and IPv6 had the same problems that IPv4 had at the time, and they had already fixed. As I mentioned before, we published these 3 documents. One of the documents is formal requirements for protocols. Now, there is still the question of, well, will this solve the problem or not? I don't know what to say. And the data point, which is not very promising, the IETF is right now shipping the DHCP version 6 specification that produces predictable IPv6 addresses, meaning, but we did what was possible, or we know what was in our hands, and we hope that this at least helps to raise awareness. That's it from my side. I don't know if there's any questions.
Thank you so much. Thank you so much for a wonderful presentation, and moreover, thanks for your outstanding work, which is even more important.
Thank you so much.
I have some questions, and we have some questions from the audience. First of all, my first question. It is very interesting to find bugs in the software, but how to find bugs in the algorithms? Are there any software or tools which help you to do that, or you just do the manual auditing and only person can do it?
Both of them. So, for example, what I do is actually I manually, audit specifications, but then at times you have like implementations that differ from the spec. So I also build tools. Let me give you an example. To sample IDs and try to analyze the IDs and figure if there is a pattern. So it's a combination of both, like manual work and try to, do analysis with tools too.
Nice. And are there any tools for that which are open source, or vendors usually close it?
Yeah, so there's the short version of the story. I did a toolkit for IPv6. So if you search for IPv6 toolkit, you will find my toolkit. And one of the things that my toolkit does, for example, is for the case of IPv6 IDs, it samples values and tries to figure out what is the algorithm that is being used to generate the values and whether they are predictable or not.
Cool. Now the question from the audience, please.
Fernando, thank you for your job. I have a few questions. Sorry for my accent. I hope you will understand me. First of all, I am security researcher. I like open source, and I like one tool. It calls diff. So I can Googled some difference in research which can help to see a vulnerability in code in some place. How can we understand it, or it's proprietary knowledge?
So I would say that if you're meaning if you can easily spot vulnerabilities on these topics, I would say that for the most part, for example, what I do, when I look at a protocol and I see that there is an identifier that is defined, I look both at the specification and I grep through the source, and you end up finding like the same stuff over and over again.
Okay, thank you. I have 2 extra questions. Why do we use IP version 6 if we have a network address translation? So, literally, why? There is one point about privacy. So, my phone's IPv4 address is not unique and the same as IPv4 address of all of these people, and there is some privacy in it that can be achieved with IP version 6.
So I will try, because this is a question that I could take like even an hour to argue, but let me provide the short version of the answer to your question. So if you go back to the 90s, okay, to the late 90s, the IETF figured that the internet was growing a lot and then we were running out of IPv4 addresses. At the same time, since there wasn't another solution on the table, the industry came up with NATs. Okay, NATs what we know and what we use every day. The IETF said NATs are horrible, we don't want NATs, we want something that is different, and the IETF said we want to provide one public address for each device from their perspective. Okay? Now what happened over time, the short version of the story, is that even after what, like 30 years, we are at roughly 50% of deployment for IPv6, which some people like to clap their hands and say that's awesome. It took 30 years to deploy to 50%, I believe it's a total failure, but it's like different viewpoint. And what I would say in that regard, that you raise a valid point, and in a lot of, from the perspective of the IETF, in a lot of cases, let's say, it's a religious topic. People will say that, no, NATs are bad, we don't want NATs, period. That's their belief, and since NATs are bad, you have to have IPv6. Then in practice, I know a lot of cases, even Kubernetes, for example. Kubernetes, if you look at the IPv6 support, it uses IPv6 and NAT. It is what it is. So there's a lot of things when you think about, like, for example, this is a topic that is technical, but at the end of the day, it involves people because it's a standards organization. And when people get involved, there's egos, there are historical artifacts, there are companies that have interests. So if you try to purely analyze the technical aspects, you are missing like 50% at least. So the reason for which we are doing IPv6 is to a large extent a political reason.
Okay, I got you, thanks. One last question. So, can we calculate a few of years when IP version 4 will die, or something like this?
I believe, unfortunately, that we will all die and people will keep using IPv4, if you want to be realistic.
Okay, thanks you. Passing the microphone.
Yes, and please, the next question.
Thank you for the presentation. In modern world, identifiers are not bound to specific hardware. For example, IP addresses may be rebalanced between different hardware, and I believe in some storage systems, even TCP sessions may be transferred from one node to another. So when providing your recommendations, do you take into account that identifiers may be rebalanced between different hardware? For example, maybe using a timer may be a problem.
So he said that I didn't fully understand.
Could you repeat in Russian and I could translate?
Maybe we'll try one more time.
Okay.
So in many systems, identifiers, network identifiers, are not bound to specific hardware nodes. For example, IP addresses may be rebalanced between servers, and in some storage systems, even TCP sessions may be transferred between different nodes. So when you provide your recommendations, do you take that into account? Because, for example, using timers may be a problem because it requires time synchronization between nodes. So maybe it's possible to provide. So maybe you keep that in mind, take that into account, and provide specifications that still work for these systems.
Yeah. So what I would say in that regard is that, for example, if you look at the IDE for which we use timers, okay, is the TCP timestamp option. Okay. In some cases, there are protocols that were designed or developed assuming that they would always run from the same instance. So nowadays that you have VMs and you migrate workloads from one place to another, that changes things. So, and there are cases where if the protocol has that kind of requirement, you have to do, let's say, some sort of synchronization, or the protocol will just fail. It is what it is.
Okay, and maybe one more quick question. Predictable identifiers is not only a problem for security, but in modern world, it's also a problem for scalability. And in many other instances, for example, in object storage systems, we don't anymore have predictable identifiers because they are harmful for scalability. It doesn't make sense to have them predictable. So don't you think that maybe for networking, we still have protocols and conventions that imply too much centralization? Maybe we need new network architectures that are more scalable, and in this case, predictability problem will be solved not only for the security reasons, but also for scalability reasons.
So that's kind of like related to the question that he had asked before. Like you could say like, well, are these protocols that we are using the right ones, or are they as good as they could be? In a lot of cases, they are not, but that's what we have on the table. Like, for example, IPv6 was developed 30 years ago. I would argue that if you were to develop a new internet protocol, it would look like completely different from IPv6. Now, we have what we have. It's like, at the end of the day, that's what we have specified, that's what the product support, and if you wanted to start from scratch with another architecture which could be valid, it took IPv6 30 years, and it only got to 50%. I don't know, I don't think we would even get to see that. It would be interesting, then there are the constraints that we have, so to speak.
The last question.
Yeah.
One more question, please. And then the last one from me.
Thank you for your speech, Fernando. I have one question. In your slides, you showed that in the same network, we use the same IP address and the same secret. And what if one day just a man in the middle appears and simply catches that address and starts using it?
So what you're saying is, what if another system starts using the same address?
No. There is an attack known man in the middle. Yeah, it's like he can just take place in our network and simply catch the exit hashed value and reuse it.
So that can happen, and for example, in the case of IPv6, there's no protection whatsoever in that regard.
So what is the point in randomization if man in the middle just can appear and steal the address?
No, let me provide some background. So if you look at how IPv6 addresses were originally specified, you configure the address by selecting a prefix, and you put your MAC address in the interface ID. So you expose your MAC address. So the only thing that we did is that putting your MAC address, exposing your MAC address to the public internet is a very bad idea. So let's replace that. Now, there's a lot of other problems that are not solved and that are intrinsic of the protocol. Yeah, there could be an attacker that takes your address. Yeah, there's no solution for that. Like, the protocol doesn't have that. So the only thing that we try to do is replace the idea of embedding the MAC address in your interface ID, of putting the MAC address in your IPv6 address, because like 10 years ago, if you had a system that connected to IPv6, every time that you had an external connection, you were exposing your MAC address. That's the only problem that we try to solve.
Okay, thanks.
Okay, no more questions. One last question from me. Maybe to engage more people in the work you do. For me, people who write RFC are just awesome. And how can individual contributors, not backed by a huge company, participate in this work? Is it hard to start?
Okay, so I would summarize, based on obviously my perspective, which might or might not apply to other people, right? I would say that first of all, one of the things that you need to do is, let's say, lose your fears. I come from Argentina. We are far away from virtually everything, from everywhere. Whenever we need to fly to some place, it takes like 20 hours. And we had this idea, and I had this idea when I started. It's other people that write RFCs, people from North America, people from Europe, and you think I don't think I will be able to write one. So what I did, first of all, study hard. And the people that produce these protocols are as humans as you are and as I am. So the protocols have flaws. What I would say is look at protocol specifications. One author that for me was like mind-blowing. There's a guy used to be a guy called Richard Stevens. He wrote a series of books called TCP/IP Illustrated. And one thing that for me opened my mind is that he would look at protocols. Like, for example, if you look at many of the networking books, they will describe protocols as if that was the state of the art, that there's nothing that can be improved. Whereas this guy, Richard Stevens, he would look at protocols and say, well, that's not a good idea. Like, people should have done something different, but that's what we have. So he looked at specifications, but also at implementations. So he would analyze a protocol, run a sniffer, and say, hey, look, in this case, this is what should happen, but look, I'm running a sniffer, and you see this other thing. For me, that opened my mind, because it was like, whoa, this thing that was supposed to be perfect, it's not perfect. So then, once you start from that perspective, like saying, okay, I don't look at protocols or RFCs like, okay, well, the guy must have been like ultra smart. You can maybe look at one of the RFCs that I wrote and find problems, and it's like, maybe I missed something. So let's say my recommendation is, whenever you approach this, don't think that the people that wrote this, including myself, is because they were smarter than you or that they are smarter than you. They just spend time working on this. So spend time, go through the specs, look at implementations, and try to analyze things with a critical mind. And you will find flaws. Probably in my own, maybe next year you will do a presentation about the problems that I introduced. So that's what I would say. Like, the people that write implementations, the people that write specifications are as humans are you or myself, and they introduce errors too. So it's like, I believe that that's the most important thing. Assuming that you could be, authoring an RFC tomorrow, and that these RFCs are not like the Bible, that it's like perfect. It's like documents that people like you and myself, they wrote. So look at them, read through them, try to analyze them with critical thinking, and that's what I did. And eventually I ended up finding problems and writing documents myself.
Excellent. That's very inspiring. And finally, please choose the best question from the audience.
So I would say that best question mean?
Best question means that the person will receive a book as a present for this question.
I go for the question about why we are bothering with IPv6. Among other reasons, because I like the idea of questioning. Why are we bothering with IPv6? With IPv6, normally you hear people that is like, we need to do IPv6. And I like that of saying, okay, why should we? Why? Okay.
Yeah, excellent. Thank you so much.
My pleasure, and it's an honor to be here.